All right, so let's go ahead and look at this is exercise 7 from section 4.1. So what's the context we're given? Along the eastern shore of Lake Michigan from Lake Makatawa to Grand Haven, there's a bike path that runs almost roughly north-south. Okay, so we're going to assume the road is completely straight. And this function s of t, which we may or may not have. No, we don't have. So we're going to construct that probably later in the problem. So the function s of t tracks the position of the biker along his path in miles north of Pigeon Lake. Okay, so we have a reference point, we have a position function. All right, so we have a velocity function, and it looks like this velocity function is comprised entirely of straight line segments. So that should help us come up with the well, let's see what we need to find here for us. Approximately how far north of Pigeon Lake was the cyclist when she was the greatest distance away from Pigeon Lake? So where is this greatest distance going to happen? So I think it's going to happen at any of the points where she changes directions. So I think I have 3 candidates here over the first 4 seconds. So where does she change directions? She's going to change directions basically wherever the velocity goes from negative to positive or vice versa. So here, here. So at 1 second, 3 seconds, and 4 seconds. So how do we find how far away she is when all we're given is her velocity? So for that, let's think about this a couple different ways and try to relate them together. Roughly, I know that over the first hour, she is traveling at a constant speed because her velocity is this horizontal line here. So I'm going to say her velocity, her S of 1 is going to be equal to 10 miles per hour times 1 hour. So that's 10 miles. So another way, actually 10 miles an hour is not quite right, is it? I think it makes more sense to say that it's 11. So 11 miles per hour times 1 hour, that's 11 miles. So if we relate that like geometrically here, we're really talking about the area under this curve. Now it's not really a curve, but trying to keep the language general for when these functions are a little more complex looking. What is the area of this rectangle? So the length of this rectangle, or the width, will be 1, but 1 what? 1 hour. And how tall is this rectangle? Rectangle is 11 units high, but what are those units of height? Those are miles per hour. So really the area under this curve does give me the distance. So I have a velocity versus time graph. And if I take areas from that graph, I'll be multiplying velocities times, which will give me a displacement or a position. So at 1 hour, this person is 11 miles away. But I said I had three different candidates, right? So now let's do this. Now, what is the distance she's started? What's the displacement she's gonna, what's the change in her position going to be in this next pair of hours here? So we said that S1 is 11 miles. What's her change in position over these next 2 hours? So I think that's going to give me S3 minus S1. So basically, my change in position from hour 3 as opposed to hour 1. So what is S3 going to be? That's going to be the area between this part of the curve and the x-axis. So that is 2 hours. But now what is the velocity? Velocity is, careful, 10 miles per hour. So that gives me a change in position of negative 20 miles. So let's remind ourselves of what what do positive values give me here? Okay, so miles north. So at 1 hour, I'm 11 miles north of this reference point, this Pigeon Lake. Um, how far am I from Pigeon Lake after 3 hours? So from hour one to hour three, I went 20 miles south. But remember, at hour one, I was 11 miles north. Should I be adding these together or subtracting? So first I went 11 miles, and then, so 11 miles, and then I basically went south 20 miles. So that's going to give me -9 miles. So here's what I'm wrestling with. I know that after 3 hours, I'm 9 miles south of Pigeon Lake. What I'm trying to reconcile is why I have a sign flip here. Let's keep going. I'll come back to that. So what happens from hour three to hour four? I'm going to be traveling north again because my velocity is positive, but how far? Um, so that displacement is going to be, I'm going to say S of 4 minus S of 3 again, but I think I have something to reconcile. Okay. What is the area here? The area is going to come from 1 hour multiplied by, it looks like 9 miles per hour this time. So that's a net of 9 miles. So what did this journey really look like? I went 11 miles north, then 20 miles. So 11 miles north in the first hour, then 20 miles south in the next 2 hours. And then 9 miles north in the final hour. Um, yeah, I think this should be S3 plus S1 and S4 plus S3. No, I take it back. Now let's look at it this way. S3 should be equal to this S1 plus this change, and that makes sense. Okay. So I'm looking at this as a net change. If I want to know what my position is at 3, then I need to know what my position is at 1 hour, and then add to that my change in position over the following 2 hours. So this gives me 11 miles minus 20 miles, and that equals 9 miles. Same situation here. S of 4 is going to be equal to, I'm calling my initial position S of 3 plus my change in position from hour 3 to hour 4. So what was my position at um, hour 3? It was -9 miles plus 9 miles. So at this time, I ended up right where I began. So approximately how far north of Pigeon Lake at the greatest distance? That happened at this time, 1 hour, and that was 11 miles north. And it actually even says, I probably should have picked up on this a while ago, approximately how far north of Pigeon Lake was the cycle since she was the greatest distance away. So this is the greatest distance away she was, and that happened to be north. All right, moving on to part B. What is the cyclist's total change of position on the time interval 0 to 2? Okay, so we kind of started answering this. but we did not stop at time equals 2, but I think now we have the means to talk about this. So I'm going to borrow our work from our last slide here. We know that at 1 hour, she was how far away? She was 11 miles north of Pigeon Lake. So then what does she do in the next hour after that? So what is position 2? Or sorry, what is her position at 2 hours? Well, it's going to be equal to whatever her position was at 1 hour, plus this change in position that happened from hour 1 to hour 2. And that'll come from calculating this area. So that's going to be over 1 hour. So from hour 1 to hour 2. And then what is the velocity over that time? It's a constant 10 miles per hour. So S of 2 will equal to S of 1, which is 11 miles, plus this area, which is negative 10 miles. And that gives me a position of 1 mile. So her total change of position was 1 mile. Is she north or south of Pigeon Lake? Well, since this is a positive number, then this implies that she was north of our reference because we have a positive value. So moving on to part C, what is the total distance the biker traveled? So distance doesn't sound terribly different, but it's actually a much different idea that we'll talk about. So basically, if I'm talking about distance as opposed to displacement, I don't care which direction I'm going. I just care about basically how far I'm traveling. So another contrast I can give you here is, if we go back to slide 1, this final result of 0 miles tells us that our displacement was 0 miles. The distance is not 0 miles. I moved. This person changed their position, and even though they changed it back, so the fact that they ended where they began is why their displacement is 0 miles. But they moved, so the distance they traveled can't be 0. So if we want to find that distance, then really what we're looking at is this. I'm going to take these areas again, but instead of this, I'm going to do this. The distance is equal to the absolute value of, what did I call them before? So the absolute value of these, 3 different areas. Now maybe I'll just talk about them differently. Area 1, area 2, area 3. So whereas in the displacement, I added up, area 1 plus area 2 plus area 3. This time I'm going to add the absolute value of area 1 plus the absolute value of area 2 plus the absolute value of area 3, which I'm not going to bother working through again because we've already found the areas. I could just take their absolute values. We got 11 miles, negative 20 miles, and 9 miles. So this will be 11 miles, not negative 20 miles, but 20 miles plus 9 miles, which gives us a final result of 40 miles. So that was one question we were asked, is the total distance you traveled. It's a 40-mile bike ride. At the end of the ride, how close was she to the point at which she started? Well, so we were asked about distance. How close was she to the point where she started? When she started, that's a question of displacement. So what was my displacement? That was, I'll say 0 miles, because this is something that even though we weren't really asked for it, we calculated in part A. All right, so our displacement was 0 miles. So if we did our math correctly, and again, we're kind of approximating off of this curve, I believe she ended up where she began. So D, sketch an approximate graph of y equals st, what s of t. I think we have more than enough data to do that. So we know that she started at Pigeon Lake. Actually, do we know that? I don't think we do know that, which means we don't really know what her initial position is, but to make this simple on ourselves, let's just say that she starts off at Pigeon Lake. And then what do we know she does? We know that the first hour, she goes 11 miles per hour. So after 1 mile, or I'm sorry, after 1 hour, we knew that she was 11 miles away. So I think the point 111 needs to be on the graph. And let's just go back to our work in part A. What happens after hour 3? After hour 3, she was 2 miles north. So after 3, she was 2 miles north. And why am I saying that? Just to be clear, because our position at hour 1 was 11 miles. Oh no, I am lying to you. Our total net position at hour 3 was -9 miles, which means that needs to be where she was. So at hour 3, she was at -9 miles, so 9 miles south of the reference. And then what else do we say? At 4 hours, she had returned to where she began. So I believe these 4 points have to be on my graph. How do I join them? Are they with curves? Well, let's think about it this way. What do we know about the way velocity and position are related? So I'm drawing the position graph. We know that velocity is a derivative of position with respect to time. These derivatives are all horizontal line segment. What does that mean? If the derivative is constant, what does that mean about the function that derivative came from? That function has to be linear, which means all of these, the connection between these dots has to be linear. So it has to look like this. So let's make sure this makes sense. So what's the slope of this line here? Well, that line goes between 0, 0, 0, 0, and 111. M equals y2 minus y1 over x2 minus x1. Slope is 11. Does that make sense with the velocity graph? It does. Our slope is 11 on the blue graph, the one they gave to us. So I will leave it to you to make sure the other 2 slopes make sense with the given velocity graph. But that should be the end of that question there.